Everybody, I hope we're doing well. Today we'll be solving Leetcode 773 sliding puzzle. So what they're asking us to do is, if we're given this configuration, can we make some movements so that ultimately we get this view here, this type of setting 1, 2, 3, 4, 5, 0. And they want to know if it is solvable, if we can get from this configuration to this one. They want to know the number of steps that it took to get there. Sorry, the least number of steps or moves. And if we cannot get there, we should return -1. Okay, fine. So what we'll do, or what's probably most or likely or a good approach, is to use a breadth first search. So let's look at this here. So I'm going to maybe close this for a moment, and we're given this initial or that example, this type of scenario here. So what I'm going to do is I'm going to place a 0 here just to make it clear. They do the same thing in the problem. So what we're allowed to do is either move to the left or up or to the right. So from this state, I'm going to call this a state, we could change the 0 here. Sorry, let's go back over here. Let's make it easier. Actually, I don't know. If we wanted to, we can make one move and move the 0 here and the 2 here. That's one. That would be one next possible state. If we were given this state, this would be one possible next state. Another way would be also to swap the 0 and the 4. So make this 0 and this 4 here. This would be another possible state coming from this one. And lastly, we could swap the 5 and the 0. So what we're going to do is use this breadth first search to basically imitate swapping or moving the 0 around, so that ultimately we end up with something like so that's the goal. We want to move the 0 around so that we want to eventually get here. Now, in order to prevent us using the same state or going back to the same state and ending up in either adding extra steps or ending up in a unneeded loop, is what we'll use. We'll keep track of each state using a visited set. And one other thing I'm going to use is I'm going to try flattening it. I'm going to flatten this matrix that they give us. So instead of dealing with it as a two-dimensional matrix, we're gonna convert it to a singular matrix, and I think that makes the problem easier. For the most part, I think that's the entirety of all I need to do is explain it. Probably more importantly, I'm going to do is walk through us with it quite clearly. So I think that'll make it very, very helpful. So here we go. One thing to notice is at every index, like for example here, if we're at this index 1 here for the 0, notice that this 0 only has 3 options. You can move to the left, to the right, or down. But on the other hand, what if we were here? Notice how 0 can only move down or to the right. So what I recommend that we do is we keep a track of the allowed movements for 0. So let's do that here. So suppose we're here in this upper left corner. We can move down. Now imagine, though, remember what I said earlier, we want to be, suppose we're at this. So this is how, suppose each of these, let me see, what's the word? These cells, each of these cells corresponds to one of these index values. So this is 0, 0, this is the first, and et cetera, et cetera. So suppose we're here in this state. Where can 0 move? 0 can move to index 1, or it could move to index, so this would be 0, 1, 2, 3. Hope that makes sense. Now, if we're here, the 0's here, 0 can move to the 0th index. It can move to 0, 1, 2, the second index, or 0, 1, 2, 3, 4. It can move down. If we're here, well, I'll just make that clear. Why not? So if we're here, 0's on the upper right corner. We could move to the left, which would be index 1, or this would be 0, 1, 2, 3, 4, 5, or the fifth index. If we're on this where the 4 is at, so the 0 could move up to the upper left, so that would be index 0, or it could move to index 4. 0, 1, 2, 3, 4, that's correct. And lastly, if we're, sorry, not lastly, if we're here, we could move either to the left, up, or to the right. So that would be, to the left would be, what is that, 3? Actually, just do 1, 3, 5. And lastly, if we're in this last spot here, this last cell, we can move to the left or up. Left would be index, is that 4? And up would be index 2. Let's just keep that in order. Okay, I'm hoping these are right. Let's just check the 0, 4, 0, 1, 2, 3, 0, 1, 2, 3, can move up. Yeah, they look good. Okay. And now, again, I said we wanted to convert this to we want to flatten it. So what I'm going to do here is I'm going to call this a state here, and I'm going to set it up something like this. So there's something called in Python called a spread operator. So I'm going to use it here. So and b zeros. So in essence, what this does is this would look something like this. It would be if this is our matrix here, it would look at like 0, 2, 3. Now we need to do the same thing for the second row. So we're going to use the star operator B1. And so now essentially this has flattened our matrix that they, or board that they provide us, the initial board. Okay. Now moving on, we'll want, I think what we can use here, there's many ways, but we use what's called a double-ended queue. So a double-ended queue, and we'll initialize that with the state. And so the way you do that is you pass in a list, or list, and then we'll just put the first state. And this first state is whatever they have provided us. Moving on, we want to keep track of, remember, we don't want to repeat work or end up in a cycle. So we don't want to visit the same place again or the same state twice. So we'll make this a set, and then we remember we need to return the number of steps, or they call it moves. I'll just call them steps, and we'll initialize that to 0. Now, so we'll keep doing this while there's elements in the queue. So right now there's one element in the queue, which is the initial state. So we'll use while queue. And I'm just gonna place this here at -1. Now let me mention this before I move on. I'm going to add an optimization towards the end, but for now I'm simply just running through it in a this is a perfectly fine manner. But at the end I'll add an optimization, and so I just wanted to give you a heads up, because I only mentioned that because we won't need this return -1 here later on. Right, so continue on where we were. So we want to look through all the elements currently in the double-ended queue. So what we can do is we can do for now. This approach may not work in another language because remember, we're going to add elements to the double-ended queue. But if you notice, we're not. If you're adding elements to the double-ended queue, in essence, this may be changing. If you're adding elements while you're looping through it, this may be adjusting, and some programming languages do not allow that. In Python, what we're doing though is we're telling Python, if for example, suppose there are well, in this case there's one element in the queue, so it's going to say for element in range 1. Even though you're adding elements to the queue, it doesn't matter. It just converts this to 1, even if you're adding elements to it. In Python, but be aware that it may not work in other languages. Okay, and we don't really need to keep track of the index. We just want to execute the for loop for as many times as there are elements in the queue. All right, carrying on. So let's remove the current state in the queue. And for the double-ended queue, we use pop left. Remember the reason why we use a double-ended queue is because it allows us to remove elements from the front of the queue. For example, so if we have, for example, if our state of the queue is, I don't know, just something like this, I don't know. That's let me just give you another example here. I don't know. So a double-ended queue allows us to remove an element from the front of the deck in constant time, instead of having to. It just makes it it's a better data structure for removing elements from the front of the queue, and for operations on the front and the back of the queue. Typically, that's not ideal for typically a list. Yes. So that's why we're using a double-ended queue. It just makes it it's a more optimal data structure for, again, removing, like we're doing here, we're removing an element from the front of the queue. On a normal list, it would be more expensive, and I can go over that later if you want to ask questions in the comments. So going back to where we left off, so this is the state. Now we want to just check if the state matches our goal. So remember, the goal is what we want it to look something like 1, 2, 3, 4, 5, 0. That's our goal, and if we're there, then we just return the number of steps and we'd be done. Otherwise, we need to keep looking. We need to keep trying. We need to keep searching, making moves with 0 in order to attempt to reach the goal. The proper state of the board that matches the goal. So what's important here is we'll always want to know where 0 is at, so that we can remember we want to know where 0 is at so we can make the proper swaps. So let's do that. Luckily, so remember, our state right now is a list. Where is it? It's a list, and the list provides a helper method or a method that allows us to locate the index of 0. And again, that 0 is the important index now, because that's where we're allowed to make moves. So we'll just call this index. Actually, just call it I. And now, so contingent upon where I is located or where 0 is located, we're allowed to make moves. So for every one of those moves, we'll go to them. So for J and moves I. So for example, if I was, I don't know, we'll just say 0, 1, 2, 3, 4. So if I is 4, 0, 1, 2, 3, 4, then at some point j would be either 1, 3, or 5, and then we perform the swaps. Okay. So we want to manipulate our state, so let's make a copy of it. And now let's swap it. Let's swap the current location of the 0 value with the possible movements that are allowed. So current I. Okay, so now we have a new state, and then we want to append this to our queue. Now we want to do a couple things now. Remember, we don't want to visit twice the same state. We don't want to, in essence, swap 0 to here, then go back to where we came from. We don't want to keep doing that back and forth over and over again. So we want to prevent doubling our work. So what we can do is make in our visited set here. What I'm going to do is store strings in there, strings of the state. So let's do that here. Let's convert this current state to a string. And we use .join. And currently we couldn't just pass in our current list because that's a list of integers, and join only works on strings. So let's convert it to a string first. So for x in current, we'll just convert this to a string. So string x, and then that should work. Okay. Now we want to make sure that we haven't visited this state before. So if s is not in v, we'll continue. Sorry, if s is in v, we'll continue. Okay, very good. Otherwise, we can add it to the queue, and let's add v to the. Sorry, let's add it, that state or the string representation of the state to our visited set. Great. And after we're done going through all the moves, we'll just increment our steps. Okay. And this all looks pretty good so far. So let's I will be adding a couple of optimizations, even though this will work. Let's maybe minimize this and open this up a little bit. Maybe a little more. So this is going to work, but what I'm going to do is I'm going to optimize it a little bit. Actually, maybe not. What happened here? Oh, this is I think I added this here. Okay, there we go. And so I'm going to just submit it. And even though it's going to work, I'm going to change this up to be a little bit faster. So this is, again, this is fine, 11 milliseconds. That's great. What I'm going to do is make this much cleaner. Okay, so what I'm going to do is I'm going to set this to a constant here. So I'm going to pull this out, and I'm going to make a goal out of this. A goal. And I'm just going to put that here. That's one thing that I think will be an improvement. Another thing I want to do is not every board is solvable. So remember, they tell us if it isn't solvable, return this -1. My suggestion is, why do all this work first, and then if there's no answer, we return -1. Let's avoid that. Let's check immediately if the board is solvable. So the sliding puzzle has something called, I think they're called invariants. So what we're going to do here is we're going to count the invariants. So what is an invariant? All right, so let's go back to the example that they give us. So an invariant is if a number comes before another number, but it's bigger, that's an invariant. And if, in this case, if there are an odd number of invariants, it's unsolvable. So let's look at this problem here. So the only invariant here on this problem is, notice how 5 comes before 4. That means there's one invariant, which is an odd number of invariants. So for this particular board, if there are an odd number of invariants, the problem is unsolvable. So let me just write that down. For this particular board configuration, when I mean configuration, I mean the dimensions. And it just so happens that this board has an even, right? There's an even number of cells. I think so. Yeah, dimensions. If there are an odd number of invariants, the board is not solvable. Okay, so let's add a check then here to check if it's solvable before we even attempt to perform the breadth first search. So what I'm going to do is I'm going to add a count here. Oh, let me just go over the invariants real quick one more time. Let me do this here, like so. For this problem here, so 1, 2, 3. Let me just change this up here. 5. Let me see, 3 and 4, and I'm gonna put a 0 here. So when we're counting invariants, we don't care about the 0. In fact, in essence, it's actually nothing. So when we're performing our check to check if it's solvable, we'll ignore the 0. So the invariants here, notice how 1 is before 2, but it's okay because it's less than 2. The only issue is here is this 5 and 3. So that would be one invariant. So 5, 3. That's the other invariant is 5, 4. So I want to make that clear here. 5, 4 is also an invariant. So okay, so that in this case it's 2. So I want to make that distinction. You count all the numbers that you're bigger than beyond it. So let's implement that here. So for I in range, and we know for this particular problem, believe it or not, it's easy because they tell us that it's always going to be 2 by 3, right? They tell us it's 2 by 3 up here. It's always a 2 by 3 board. So we'll keep that in mind when we write this loop here. For I in range 6, for j in range. Now we only care about the elements afterwards. So let's use I plus 1 here, and we'll also go to 6. And remember I said we don't need to worry about the zeros when we're counting the invariants. That doesn't count. So we'll make sure to skip that here. So if state I equals 0 or state j equals 0, continue. Otherwise, if state I is bigger than state j, and remember this I comes before this j because remember j starts at I plus 1, so it's after it. Then we just increment count. Okay. And now all we need to do is remember, if there's an odd number of invariants, the board is not solvable. And I encourage you to look this up online too for verification. If count and 1, that means this is just a bit operation to make sure to check if this is odd. Return -1. So now that means I can remove this bottom -1 here, because what we've done here is we're checking if the problem is solvable. If it is, we're guaranteed to return the steps here, and then we don't need an additional return statement down here. All right, so let's check it locally. Cool, it looks good. And this runtime should be faster than the other time. I hope. We'll see. We'll find out. Cool. 3 milliseconds. Sounds good to me. If you have any other questions, let me know. If you liked it, let me know. Just so you know, there is another approach for solving for example, a bigger board. If you'd like to know, or let me know, ask me in the comments. Other than that, have a great day. I hope this video was helpful and you learned something. If not, I apologize. Take care.